Okay, now we want to start making some measurements, and the first thing we need to do is set up our compass. The compass measures magnetic north, and we want to make measurements relative to true north, and in general these two are different. And the difference is called the magnetic declination. This map shows the magnetic declination across the US, and you can see along this line the magnetic declination just happens to be zero, but everywhere else it's not zero. Over to the east of this line, the magnetic north points to the west of true north, and over here it points to the east. This symbol here is often shown on a topographic map. It shows the magnetic north here at an angle and true north pointing straight up on the map. And so we need to adjust the compass to account for this. Now the value that we use for the declination should be the current value, and the magnetic declination changes with time. The magnetic pole is moving, and as a result the declination changes, and it can change by a degree or two over 10 or 20 or 30 years. And so often old maps have declinations that are noticeably different than the current declination. So you should adjust for this, and the thing that would be the best approach is to go online and you can find the current magnetic declination for any place on Earth, and so check it out, find out the current value, and use that to set up your compass. When I did this in 2012, the declination for Clemson was 5 degrees 56 minutes, just shy of 6 degrees. So to set up the compass, this is a Silva compass, and what you should do is rotate the outer bezel of the compass so the north on the bezel is pointing with this alignment point. And then you can adjust the internal scale, which is going to be reflected in this red arrow. See the red arrow inside of the compass. There's a little screw on the back of this compass, and you can rotate the screw and move that red arrow relative to the black bezel. There's a little gear in there, you can move it around. And different compasses are set up somewhat differently, but this is the basic principle. So what I've done is to set up the outer bezel so it's pointing towards true north, and then I've set up the inner reference arrow, the red arrow, so that it is pointing in this degrees 9 degrees west. So this would be set up for a declination of 9 degrees to the west of north. And let's see, that should be 9 degrees right there. And so what's going to happen when I make a measurement, I will line up this red arrow here. I'll rotate the bezel so this red arrow that's inside of the compass lines up with this red arrow that moves with the magnetic field. I line those two up, and then I read the bearing where off of the bezel where this tick mark is. So you can see that if I were to do that with the current reading, if this red arrow was pointing right along this red arrow, then I would be pointing true north. The magnetic arrow would be pointing 9 degrees to the west, but if I had a declination of 9 degrees, then I would be pointing, in fact, true north. So go ahead and try setting your compass up with the declination for Clemson. Okay, now once you've got the declination set up, you're ready to start making a measurement. There are a couple of different approaches for doing this, and one would be to make a measurement by waist level sighting. And to do this, you'll hold the compass down at waist level, and the compass should be fairly level. Some compasses will have a bubble level on it, and so you can ensure that it is indeed level. This particular compass doesn't, so you have to just manually hold it approximately level. And then what you do is use this mirror in the cap of the compass. The lid opens up and there's a mirror right there. So you look down and then you line up there's a little line on that mirror, and you line up that line and these tick marks here, and there's another sighting tick mark here. You line those up and you point that at the thing that you want to get the bearing to. So you would be looking at your target in this mirror. And when you do that, the red arrow will move around and get oriented in the magnetic field. And you can see here that it has this orientation. And then you turn this outer bezel so that the red arrow on the inside, this arrow shown right here, so that arrow moves around and lines up with the movable red arrow. So do that, and do that while you're sighting, and then once you've got it in place, you can pick the compass up. The reading will be done off of this bezel, and the reading will be where this mark here, this little tick mark, intersects the scale on the bezel. So once you have it lined up while you're aiming it, while you're pointing it, once it's lined up, then you can move it around, and even though the red arrow moves, the alignment with the bezel won't move. So in this case, the azimuth would be 48 degrees. So another way of doing this is to sight the azimuth at shoulder level. So to do this, you should position the mirror at approximately 45 degrees, hold the compass out at arm's length, and the compass itself should be level. And then you will sight at the target through this little opening right here in the compass. And there's a little line that goes right down the middle of that opening, and that line should be lined up with this little tick on the compass, and you should be looking at the target out beyond. So you get all of those lined up, and then you need to turn the bezel, which you can see through the mirror, and you turn the bezel so that the magnetic arrow on the inside is lined up with the red arrow that you're moving with the bezel. You get those lined up, and then you have a reading. You can then bring the compass down and read off the tick mark. Now keep in mind that when you do this, the bearing that you're looking along is read over here. And there's a little tick mark there, and where that tick mark lines up with the scale on the bezel is your reading. The previous application, where we were sighting it at waist level, we were looking in a different direction. We were looking actually in that direction, and in that case we used this tick mark. Okay, so it's important to keep in mind which tick mark you should use. One of the things that you need to keep in mind is that the magnetic sensor on your compass, there's a small magnet on the tip of the needle, that it will be attracted to ferrous materials, and this can cause an error in the measurements. And so here's just an example. If you're making a measurement and there's a car, I don't know, 8 feet away or so, there's probably not going to be much of an effect. But if you move the compass over right next to the car, you can see that the red arrow is pointed in this direction. And then when we move it near to the car, the red arrow is now pointing right there. So it makes a big difference. So don't be right up next to a car. It's fairly obvious, but if you don't know it, then it can cause trouble. Also, here's another case where I'm making a measurement and there's a rock hammer right there, and the rock hammer is ferrous, and that can cause a problem. If you're measuring with the compass down at your waist and you have a steel belt buckle, then that could cause a problem. So just keep this source of error in mind. Okay, now we want to try to get a handle on the uncertainty or the precision of the measurements that we make. And so what I would recommend is that you become familiar with your compass, try using those two methods of measuring a bearing, practice a little bit, and then go and pick out a point off in the distance that you can see easily and measure the bearing to it. How repeatable is the measurement that you're making? So what I'd recommend doing is make 5 or 10 measurements of the bearing to the same location. Try doing it with the compass down at your waist or out at arm's length, or try both. Write these measurements down and then determine the coefficient of variation. And you do that by determining the mean of the measurements, the 10 or 15 measurements, determine the standard deviation. And the coefficient of variation, this is simply the standard deviation divided by the mean. The standard deviation is expressed then as a fraction of the mean. So this will give us an idea of how repeatable the measurements are. Okay, now the other method that we need to come up with is a way of measuring distance. And a simple way of doing this is by pacing off the distance. This works well for distances that are in the tens to hundreds of feet, and that's often a distance that we come up against in the field. So what I would recommend is that you calibrate your pace. If you do that, then if you're careful, you can have a tool that allows you to measure distance that you always have. Just your normal pace will serve to give you a distance measurement. So the procedure would be to lay out a known distance, say 100 feet, and pace along this distance 5 times or perhaps more, but at least 5 times. Use a comfortable pace that you can duplicate. Write down the number of paces for each time that you do this, and then determine basically a calibration factor. So you determine the distance per pace. That would be, in this case, 100 feet divided by the number of paces. And this will be a calibration factor. So if you know that factor and you know the number of paces, then you can multiply the two together to get the distance. This will be something you should write down, and hopefully it ends up being a calibration factor. The distance scale could be in feet or meters or yards, depending on what works out to be convenient. In my case, my pace is about 90% of a yard. So I can take my paces, take that many yards and subtract off 10%. That's what I would recommend doing, coming up with this calibration factor, and also determine the coefficient of variation when you make these measurements, because that'll give you an idea then of how uncertain the measurements that you get from pacing will be. I guess one thing too that I should keep in mind is that generally when you do this, you lay out a tape on some nice, smooth, even ground, and in that scenario, the pacing is pretty easy to have it be quite repeatable. Often in the field, you're pacing uphill or downhill or over obstructions, and you can have additional errors that you encounter. And so one thing you might try is laying the tape out over some rougher terrain and try getting the coefficient of variation for that scenario as well. So the application then will be to pace from one location to another. So as you're making your map, you would have one base station and you would pace over to the next one, record the number of paces, and then you can multiply by your calibration constant and record this distance. Now, what I would strongly recommend is that you write down both the number of paces that you've counted and the distance that you calculate. You'll be primarily interested in the distance, but I would urge you to write down the number of paces, because it's pretty easy to make a calculation error, particularly if you're doing this in your head. And if it turns out that there is an error and you have to trace it back and see if you can find it. If you have the actual number of paces that you counted, you'll be able to figure out, you'll be able to find the error. But if you don't write down the number of paces, all you write down is your calculated distance, then you won't be able to find that error, and you may have to go out and remake the map. We'll be interested in how accurate the pace and compass method is. So if we've started here at this point and we've measured a distance and an angle over to that point, and we've plotted the point, what kind of errors do we have in the location of that new point? Well, there'll be two sources of error. One will be in angle and one will be in the distance measurement. The angular measurement will result in some uncertainty. The direction could be that, there, or somewhere in between. And we've measured the coefficient of variation in a previous exercise. And so if it's 2 degrees, then this error, this distance, will be 2% of the total distance here. If this is 3 degrees, then it'll be 3%, and so on. And that'll work for relatively small angles. So that'll give us a way to estimate the lateral error. And then we'll also have errors in the distance measurement. And that'll come right directly from the coefficient of variation of the distance measurements from pacing. So we did multiple paces, and we've got a calibration constant, and there was some variability in establishing that constant. And if we go back and take a look at that coefficient of variation, that will give us a measure of the uncertainty of the distance. So we would have, in this particular case, we would have 2% of the distance error in a lateral measurement and 3% error in the measurement along the distance itself. So that'll give us an error, something like that. We locate the point in the middle, but we have some uncertainty, and we have some way to estimate how much uncertainty there is in the location of that particular point. So each time we make these measurements, we'll have some uncertainty associated with that measurement. And it's important to keep this in mind when we try to assess the overall uncertainty of the map that we've made.